Hi, my name is Sudipta, and this is my Physics 2212 Lab 2 magnetic field of a bar magnet. So the purpose of this lab is to determine the distance dependence and magnetic dipole moment of a bar magnet using experimental data and to create a computational model that visualizes the magnetic field around the bar magnet. So for my results, I found that nu equals 1.16 m squared. For n, I got negative 3.1074, and I found that the magnitude of the net magnetic field increases as distance decreases. So the main fundamental principle used in this lab was Biot-Savart law, which relates the magnetic field of an object in teslas to the current running through the objects and the distance between the source of the field and the observation point. For this lab, I assumed that the bar magnet acts as a magnetic dipole, and the four formulas underneath are all derived from Biot-Savart law and will be used in the calculations for this lab. So for this experiment, I assumed the system to be the magnet and the surroundings to be everything else. And for the initial conditions, we had the bar magnet and the magnetometer on the phone. So the location of the magnetometer on the phone was pinpointed by sliding the phone perpendicularly to the ruler, both vertically and horizontally, with the bar magnet on one end of the ruler in order to see which position of the phone relative to the strongest magnetic field was being read, as shown in the top figures. The on-axis distance from the bar magnet to the magnetometer was found using the ruler for several different magnetic field values, as shown on the right. The values were then linearized by taking the natural log of each side and then graphed, as shown on the graph on the right. And this is the linear equation. And then I found the off-axis magnetic field of the bar. So for D in meters, I found it to be 0.2286, and then B net I got 6.982 times 10 to the negative 5. So I found that when the magnetometer is far away from the magnet, it measures the near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. The position of the phone matters in order to make sure the magnetic field of the Earth does not interfere with the readings for the magnetic field of the bar magnet. So for my calculations, I used the distance dependence equation, I used the linear equation, and I found this slope n to be negative 3.1074. I set ln k equal to the y-intercept, and I calculated the value for k, and then I used Biot-Savart law to find nu. So r, the distance was 1 meter, and then I set the Biot-Savart law equal to the distance dependencies, and I solved for nu. And this is my code for the glow script. We had 6 observation points, 2 on axis and 4 perpendicular. And this is my output, which calculated the magnetic field at each observation location. So this is as you can see, my measured data and the data from the simulated magnetic field were fairly similar, and the directions did match because the magnets and the magnetic dipole acted similarly. Some sources of error include the nearby electronics distorting measurements with their own magnetic fields, movements of the phone during measurement, and imprecise location of the magnetometer found on the phone initially. So what if in the experiment we didn't orient the setup to compensate for the magnetic north? Well, then both the x and y components would be different and inaccurate because the magnetic north is not accounted for. The magnetic north contributes to both magnetic field components, but the z component would not change as the meter stick is laid flat. So if we redid the experiment, but instead of using a single magnet, the two identical magnets stuck together end to end, the magnetic dipole moment would be a different value, and the magnetic field magnitude would increase to approximately double, which causes the measured distance for each magnetic field to decrease. Thank you.